Hi, everyone. My name is Lindsay Dever, and I'm a new faculty member at Millersville University. And today I'm going to talk to you about bias in the distribution of holonomy for compact hyperbolic three manifolds. So in the first talk, I'm going to focus on some of the geometry, what even is holonomy, and some of my results on the distribution of holonomy. And then in the second talk, we'll go more into the spectral to geometric correspondence and how that's used to prove some of these results. Okay, so let's get started. Okay, so first I want to start off with an analogy. So this is the regular old prime numbers. And what we're going to do is we're going to sort them into two categories. So we'll sort them into categories of primes that are congruent to 1 mod 4 and primes that are congruent to 3 mod 4. Okay, so if we keep track of how many primes are in each category, we have 3 and then 5, 7, 11, 13, 17, 19. And we can notice that there's roughly the same number of primes in each category. Okay. So the way we say this formally is that the prime numbers are equidistributed between equivalence classes 1 and 3 mod 4. Okay, but now let's count again, and we're going to keep track instead of just whether they're even, we're going to keep track of which category is winning at any particular time. So first we add 3, and so 3 mod 4 is winning. And then when we add 5, the two categories are tied. And then we add 7, so 3 mod 4 is winning again. And then 11, and then when we add 13, 3 mod 4 is still winning. And then we're tied again. So I'm going to keep going. And you'll notice that 3 mod 4 is usually winning. So the way that we describe that is we say that there's a bias towards 3 mod 4. So even though there's roughly the same number of primes in each category, 3 mod 4 is still winning the race. So this is often talked about as the primes race. Okay, so the way we formalize this is that we count the number of primes up to x. And then we count the number of primes that are congruent to, for example, 1 mod 4. And this is kind of a funny way to write it. But since we expect half of the primes to be 1 mod 4, we can look at double that amount and subtract it from the total number of primes. And since there's a bias towards 3 mod 4, we expect this value to be negative. So if you want to pause and think about that, you can think about why that would be the case. Okay, so to take this another level, we can start to think about not only which category is winning, but we can also think about the distribution of how much either category is winning. And the way we quantify that is this difference. That shows how far ahead or behind the category of 1 mod 4 is. And it turns out that this is the appropriate normalizing factor. And once we multiply by that normalizing factor, it turns out that this is actually distributed according to a probability distribution. So this was shown by Rubinstein and Sarnak. And with the assumption of generalized Riemann hypothesis and grand simplicity hypothesis, they showed that this normalized bias count is distributed according to this solid line. And then the jagged line is a histogram of actual data from large prime numbers. So we can see that this is centered around -1, which means that there's a bias away from 1 mod 4 and towards 3 mod 4. Okay. But we will notice that there's this tiny little tail that's positive, and that's the part where 1 mod 4 catches up and is actually winning. So that happens a non-zero percentage of the time. Okay. So now I want to get into some of the hyperbolic geometry, so we can get to see how equidistribution and bias plays out for this holonomy parameter. Okay, so I'm working in hyperbolic 3 space. So one way of representing this is the upper half space model, where you have a complex number, so you have x plus iy, and then you add a positive height r. And we give this the non-abelian multiplication, where ij is equal to negative ji. So you can think of this as a subset of the Hamiltonian quaternion algebra. And then we give this space the hyperbolic length metric, where we take the infinitesimal Euclidean length and divide by the height r. So if we take a fixed Euclidean length and move it towards that complex plane, that would be blowing up in the hyperbolic sense. And this will also induce a hyperbolic volume. And if we look at what the geodesics are, so the geodesics will give the path of shortest distance from one point to another. And these turn out to be half circles and lines that are orthogonal to that complex plane. Okay. Okay, so once we have a metric, we can talk about isometries. And it turns out that the orientation preserving isometries in this space can be written down with an explicit map, where P maps to AP plus B times CP plus D inverse. And that's using that weird non-abelian multiplication that I talked about. And if we just take these coefficients, A, B, C, and D, off of this map and put them in a matrix, it turns out that that will correspond to a complex valued matrix with determinant 1. And if we then mod out by plus or minus the identity matrix, this will actually be a 1-to-1 correspondence, which is why we're working with PSL2C instead of SL2C. That just means that we've identified plus or minus the identity. And it's kind of a fun exercise to check why the identity and minus the identity would give you the same isometry. Okay. Okay, so if we take a discrete subgroup of these isometries, that will correspond to a hyperbolic manifold or orbifold, which we'll write as H mod gamma. So this is a picture of an example from the program SnapPy. And this is a solid 3-dimensional object where we're gluing faces of the same color by some isometry in gamma. Okay. Okay, so it turns out that the condition that H mod gamma is a compact manifold is equivalent to asking that every non-trivial element of gamma is conjugate to a diagonal matrix that is non-torsion. So these are the kind of manifolds that I work with. Okay, so if we have one of these isometries, it turns out that it will leave a single geodesic invariant. So I'm just going to draw that onto this picture. So we're thinking about what these isometries do geometrically. And it turns out that it will keep this geodesic invariant, which means that if we act by gamma, P will map to some gamma P that is also on that geodesic. Okay, so what this means is that in the quotient space, H mod gamma, P and gamma P will be identified. So this isometry will correspond to a closed loop in our hyperbolic manifold. And that will have some finite hyperbolic length, which we write as L of gamma. But we can also see in this picture that there might be some twist around the geodesic. And the angle of that twist when those 2 points are glued together is called the holonomy of gamma. Okay. And these can also be read off of the diagonal matrix that gamma is conjugate to. So they can be read off of here. Oops. And sometimes you might hear this referred to as the complex length. Okay. So to make sure we're visualizing this correctly, a hyperbolic isometry is one that has 0 holonomy, so there's no twist. And then a loxodromic isometry would have some non-zero twist. So the holonomy would be non-zero. Okay. So a major problem in this area is counting geodesics. So, okay, so here's an example from the Weeks manifold, and this is some data from SnapEye. And what we want to do is we want to count the number of closed geodesics with length up to y in our manifold. So this manifold has 6 geodesics up to length 1, 9 geodesics up to length 2, and so on. And as we can see, this number is increasing very quickly. Okay, so the prime geodesic theorem gives us an asymptotic count of the number of closed geodesics up to length y. And okay, and this version with the explicit error term was proven by Sarnak in 1983. And it says the number of geodesics up to length y and our hyperbolic manifold is equal to an exponential integral plus an error term of about e to the 5y over 3. And this funny notation, this means that this is less than or equal to a constant depending on gamma and epsilon times e to the 5y, or let's get this precise, 5/3 plus epsilon y. Okay, so this is an error term that's less than or equal to a constant times our exponential. And then this whole thing together is asymptotic to e to the 2y over 2y. Okay. So what I'm interested in doing is counting geodesics not just by their length parameter, but also by their holonomy parameter. So for example, we could count the number of closed geodesics up to length y with holonomy in an interval of for example, from 0 to pi. So if we compare these two columns, we can see that if we restrict holonomy to this interval, we're getting about half the number of geodesics than if we look at all of the closed geodesics up to length y. And this makes sense because our holonomy interval is from 0 to pi, which is half of all of the possible angles between 0 and 2 pi. Okay, so this can be formalized, and this was proven by Sarnak and Wakayama in 1999. So they showed that if you have an interval of holonomy, then the number of closed geodesics with length up to y and holonomy in I is asymptotic to the length of the holonomy interval times the total number of geodesics up to y. So this is another way of saying that holonomy is equidistributed throughout the circle. So this angle is equally likely to land in any interval of a given size. Okay. And I should say that this was proven in a much more general setting of locally symmetric spaces of finite volume and negative curvature. Okay. So in 2014, Margulis, Mohammadi, and O further generalized this result to Zariski dense spaces. And they also proved a small unspecified power savings in the error term. Okay. All right, so the moral of the story is that holonomy is equidistributed. Okay, so together with my advisor, George A. Milicevic, we specified to the specific case of compact hyperbolic 3 manifolds, and we were able to prove a stronger result in this setting. So we showed that this count of geodesics with length up to y and holonomy in the interval I is equal to our main term plus an error term of e to the 5y over 3. And we want to compare this to our main counting term, which is asymptotic to e to the 2y over 2y. Okay, so we have a power savings compared to that main counting term. And the nice thing about this is that the error term depends only on the group gamma. It doesn't depend at all on the choice of holonomy interval. Okay, so this allows us to choose our interval to be changing or even shrinking. So I'll give an example of what I mean by that. Okay. So essentially, since this term is asymptotic to e to the 2y over 2y, that means we can shrink our holonomy interval up to e to the negative y over 3 and still have the main term be larger than the error term. Okay, so let's look at an example from the Weeks manifold. And we're counting, I'm plotting the holonomy as an angle on the circle. And we're counting the number of geodesics that fall in this red interval right here. So this is geodesics up to length 3, up to length 4, and up to length 5. And our result says that the number of geodesics that fall in this interval is proportional to the size of that interval. So this is a stronger result than just equidistribution alone. Okay. Okay, so now that we have equidistribution, I want us to think a little bit about the question of bias. So my first attempt at asking about bias was to think about whether there's more geodesics on the left half of the circle than the right half, or with holonomy on the left half of the circle. Okay, so the idea was to count geodesics with holonomy between pi over 2 and 3 pi over 2, and that's our left side, versus geodesics with holonomy between negative pi over 2 and pi over 2, which is our right side. And so we know from equidistribution that these should be roughly the same, 50% on each side. However, we can still subtract them and then see which side is winning. So when I do this, my data was saying that this was almost always positive. So the left side was usually winning. However, it was really hard to prove anything in this setting with sharp cutoffs. Analytically, it's much easier to work with smooth cutoffs. And you'll see why in my next talk. Okay, so I smoothed out this question. So instead of doing left minus right, I'm measuring cosine of the holonomy, which is still capturing the tendency towards the left or right side of the circle, but now just in a smoothed way. But this sum still has a sharp length cutoff. So instead, we're going to sample length with a smooth function that approximates a sharp cutoff at y. And eta tells us how big that ambiguous region is where our smooth function is decaying. Okay, so we have the smooth version of this question. And then for technical reasons, it turns out to be easier to sample, to multiply each term by the length of the geodesic as well. Okay, and then we normalize both of these sums. And these just turn out to be the correct normalization factors, dividing by e to the y over y for the first sum and dividing by e to the y for the second sum. Okay, so we want to know, is this typically positive, meaning there's a bias towards the right side of the circle, negative, indicating a bias towards the left, or is this typically 0, meaning that there's no bias? Okay, so here's some numerical data. And this is for 3 different manifolds, sampling geodesics of length up to 8, which is about 500,000 geodesics. And we're looking at the distribution of these sums. And what I want you to notice is that these sums are not centered at 0. So they're typically negative. So this is 0. And they're typically centered around -2, which would indicate a bias towards the left side of the circle. Okay. So we can see this also through the mean values of these sums for the different cutoffs. Okay. So I was able to prove that there is in fact a bias. So the average value of this normalized sum is typically -2, but it could be pushed in the other direction, depending on the number of spectral parameters that are equal to 0. Okay, so I haven't told you what a spectral parameter is, but I'll talk about that in part 2. But right now, what we're taking away is that there's typically a bias. Okay, so I have a more general version of this problem where we take, instead of just sampling with cosine for left versus right, we can sample with any smooth function f on the holonomy that averages to 0. So we can measure bias towards or away from any part of the circle. Okay, so we define our sum. So this is our bias count. And then we can normalize this by dividing by e to the y to get our normalized bias count, which we write as E of FG. And remember, G is the smooth length cutoff. Okay, so I was able to prove what the average value of this sum is. And it might look a little scary. So it has all of this spectral information that we didn't talk about yet. But in the typical case, where this would be 0, we have that this bias is entirely controlled by this, which is equal to 1 over 2 pi and the integral from 0 to 2 pi of f of theta cosine theta d theta. So basically the entire bias is being controlled by this tendency towards the left side of the circle. Although other biases could potentially be introduced if there are 0 spectral parameters. Okay. Okay, so I also showed that this bias is distributed according to a probability distribution. So this is the analog of Rubinstein and Sarnak's results, where they have their nice graph of what their normalized bias count looks like. So I do have a probability distribution. And if my spectral parameters are linearly independent, I can write down the exact probability distribution function for how this count is distributed. Okay, so this might look very scary, but it's given by this integral over J0 Bessel functions, which are well understood. And then the only thing that is still mysterious are these multiplicities of representations. So I'm going to talk about what that means in my next talk and why that shows up. But the moral here is that we have a distribution and it's symmetric about our bias constant. Although I do want to warn you that the hypothesis of linear independence isn't always met. Okay, but if it is, we have this really nice case. Okay, so I'm going to stop there. Thank you so much for listening. And if you want to hear more about the spectral to geometric correspondence and Selberg's trace formula, I'm going to talk about that more in my next talk.